Hi, everybody. In this video, I want to talk more about other types of roots. So these could be your cube roots, your fourth roots, fifth roots, etc. And again, we've done a little bit of this in a previous video, but I want to bring in some more examples here and just do a little bit more practice. All right, so let's go ahead and start with that. So let's just kind of review a couple examples for simplifying. So maybe the cube root of 64 and the fifth root of -32. So remember here, instead of looking for perfect squares, we're looking for perfect cubes or perfect fourths or fifths, depending what it is. So when there is a number written in here, this is called your index. And this is your type of root. So here I have a third root. Here I have a fifth root, right? So in this case, we're looking for a number such that when we raise it to the third power, we get 64. And here we're looking for a number to the fifth power that gives us -32. And you can play around a little bit with different values, and hopefully you'll see that, well, 4 to the third power is 64, 4 times 4 times 4. And -2 to the fifth power is -32. -2 times -2 times -2 times -2 times -2. So if you multiply those all out, you do get those values. So our answer here for the cube root of 64 is going to just be 4. And then for the fifth root of -32, it's going to be -2. So it's the same sort of idea that as we deal with square roots, but you're thinking about higher power. So what value to that higher power is going to give you that final answer. Okay. Now, one thing to note, if your index is odd, then again, when you have something where you have the same exponent to the same root, they do cancel out. So you just left with that inside value. But if your index is even, then you end up taking the absolute value of that. Okay, so remember, the kind of the takeaway here is that an nth root and nth power cancel out. And then you just have to be careful. So sometimes we take the absolute value, sometimes we don't. But remember, you can always use order of operations. So if you simplify inside first, then you should still get the right answer. The other thing we have is that the power in quotient rules apply here as well. So for instance, if you have the nth root of a times b, you can go ahead and split that or bring it back together. Or if you have the nth root of a over b, again, you can go ahead and split that or bring it back together. And of course, assuming here that b is not 0 in this, this denominator. Let's move that up so you guys can see that. And just like before, for adding and subtracting, you would need the same kind of root. So just like with square roots, you can also add and subtract other roots, but it has to be exactly the same. So just a little bit harder, a little bit more work to just watch those roots and make sure you're using the same exact root if you're adding or subtracting. But just like with square roots for multiplication and division, you can really separate them out as much as you want or bring them back together. So let's do something like the cube root of 24. Now, if I think about the cube root of 24 and I try to think about, okay, is this a perfect cube? It's actually not. If I try 2 to the third power, I get 8. If I try 3 to the third power, I get 27, 3 times 3 times 3. So I'm skipping over 24. There is no perfect cube there. So just like with your square roots, we do want to simplify it as much as possible. And what you want to do is think about your factors. So just going to write out all my factors here. And this time, instead of looking for square roots, we're going to look for cubes, right? Instead of looking for squares, we're looking for cubes here because my index is 3. And 8 is a cube, right? 2 to the third power is 8. So we're still going to simplify like we did with squares, but you're thinking about different powers now. So this becomes the cube root of 8 times the cubed root of 3. 8 times 3 is 24. And then that cubed root of 8 is 2. So you have 2 times the cubed root of 3 as our final answer here. Okay. Let's do another one. So I'm using that product rule. Oh, sorry, I wrote power. I'm sorry, guys. This is product, not power. There we go. That looks better. All right, let's go to a new page for another example. Okay. So here I'm dealing with fourth roots. So you're thinking about things to the fourth power. I don't have a value that is a fourth power that's 8, right? 2 cubed is 8, but not 2 to the fourth. 2 to the fourth is 16. I don't have anything that's going to work here. So what I'm going to try instead is let's bring them back together. They're both the same kind of root, so I can go ahead and bring these back together. So 8 times 4, which is 32. And now let's try again. So here I'm looking for a fourth, so a fourth power in my factors. So I have 1 times 32, I have 2 times 16, and I have 4 times 8. And I actually do see a power of 4 here, which is 16. 16 is equal to 2 to the fourth power. So if I see that power that I'm looking for, I'm going to keep simplifying. So I do the fourth root of 16 times the fourth root of 2, because 2 times 16 is 32. This piece becomes 2, and then I'm left with the fourth root of 2 as the rest of my answer. Okay. Now for this one, I have the fourth root of 81 over 16. If I think about 81 and 16, I don't really see anything I can do there. So I would see, can I divide these? Can I simplify? There's not really anything going on. But what I could do is I could split this, right? So I could split my root. And actually, these now both come out perfectly even. The fourth root of 81 is just 3, because 3 to the fourth power is 81. And the fourth root of 16 is just 2, because 2 to the fourth power is 16. So even though I couldn't do anything initially, if I split, I was able to simplify both. So sometimes we go back together to help us simplify. Other times we're going to split that root to help us simplify. But remember, it only works when multiplying and dividing problems. If we have something like adding and subtracting, let me do that next. So remember, can only add or subtract like roots or like radicals. So these are different. They're both cube roots, which is good, but one has a 16 and one has a 2. So I can't do that. But I can try simplifying. So if I think about 16, I have 1 times 16, I have 2 times 8, and I have 4 times 4. Now I'm looking for a cube here, and the one that works is the 8, right? Because 8 is equal to 2 cubed. So I can split this. The cubed root of 16 becomes the cubed root of 8 times the cubed root of 2. And then this piece becomes 2. You're going to notice that roots blow up, exponents make that number blow up very quickly. So if you have higher power roots, a lot of our answers are smaller numbers because they grow very fast once we start multiplying them out. So what this becomes, that 5 cubed root of 16 minus 11 cubed root of 2 becomes 5 times, and then this gets plugged in here. So 2 times the cubed root of 2 minus 11 cubed root of 2. I multiply those outside numbers, I get 10 cubed root of 2 minus 11 cubed root of 2. And now notice I have the same kind of roots. So I can do 10 minus 11 here, which is -1 times the cubed root of 2. You don't really need the 1 there, so you can also write it as just negative cubed root of 2. And remember that this is being multiplied. So I know it looks kind of funny to write it this way, but it's actually -1 times the cubed root of 2.